In previous lecture, we have good morning everybody. Today I will start line size, and this topic is taken from Surface Production Operation book, Stewart Arnold book, GPP, God Publishing House, Volume 1. Okay. In the previous lecture, we have seen that if we have any pressure vessel, so different end condition or head condition changes its weight. Okay. So, head condition thickness will be changing your weight. So, when weight is changing, your cost will be changing, your operation strategy also will be changing. So, you have to optimize what will be the minimum weight possible and minimum cost possible. Based on this, actually you are buying or buying any separator system or high pressure system. But whenever you have lines, pipes connecting to separator or transporting fluid from one point to another point with high pressure, so that design consideration also you have to consider. Uh, Here, because the pipe and pressure vessel two different thing actually, because pressure vessel is having end, in pipe we are assuming there is no end. So, design there will be certain changes. Okay. So, let us see what the formula says. So, when you are choosing line thickness, so you have to consider, so line size criteria, both pressure drop del P and flow velocity V needed to be to choose line size. Okay. Normally del P or pressure drop is not main criteria for pipe in piping design. Most pressure drop occurs across a control valve, because you have one pipe and you have one valve or any other mechanism fittings, so their pressure drop will be more, because whenever there will be laminar flow, laminar boundary layer and smoothly fluid is flowing through straight path, so pressure drop will be very low. But if there is any bend, so you can remember in previously I told in previous other lectures that whenever there is any bend, okay, or any fittings in nut bolt, or it is changing size of pipe, directly expanding or directly in contracting, suddenly expanding, fittings are there. So, in that case your pressure drop will be higher. Okay. So, normally there will be not main criteria for piping. Okay. Yeah, first you have to consider the most important part, for example any fittings, valves, notch or any change in flow direction, those things first you have to consider. Then after that you can consider pipe friction total. Okay. So, del P is important for long pipeline equipment operating at same or nearly same pressure, flow between low pressure and atmospheric pressure vessel, equivalent length and equivalent and elevation changes are there. So, in that case del P should be considered. And line diameter, so velocity, fluid velocity minimum fluid velocity and maximum, okay, fluid velocity will be deciding your pipe velocity. For example, you want to pass fluid through a pipe and you are creating very high pressure. So, in that case very high pressure drop also will be possible, because friction pressure drop FLV square by 2GD formula is there. Okay, right. So, if you are changing fluid velocity at very high level, so what will happen, your pressure drop will be increasing. Okay. And how to change this fluid velocity? So, if you enlarge piping diameter, so flow rate equals V into A, right. So, you let us say you are getting very high fluid velocity and flow rate is not changing. Flow rate will not be changing through the pipe, because we are assuming you are not destroying mass and it is non-compressible flow. So, in that case if you are changing flow area, then velocity must be changing. Even gas case also same thing will happen. If you are changing flow area, then velocity will be changing. Okay. So, velocity if you reduce, then your del P or pressure drop also will be reduced. Okay. So, whenever you are designing any pipe, you have to consider fluid velocity. Okay. So, that will be giving your pipe sizing. So, minimum maximum. And what will be the minimum pipe size? Minimum pipe size will be decided based on your solid is there. If solid there is a small sand particle, if you are reducing fluid velocity, what will happen? Sand settlement, you can remember. Sand particle will be settled in the pipe. It will be creating one layer. So, slowly that layer will be increased, certain after certain time it will be getting blocked. So, if you are getting very low flow velocity, sand particle will be blocking your path actually after certain time. But if you are increasing flow velocity, it's very high rate, then a pressure drop will be there. Then you have to optimize what will be your optimal pressure drop or optimal size, so that you can use your pipe or high pressure pipeline safely, and it will be giving a long term efficient transportation. Erosion, noise, water hammer, limit Vmax. So, if we have very high velocity, then erosion also possible. What happens at very high velocity, that sand particle or solid particle will be hitting the metal continuously. When metal particle is continuously hit, so micro particle will be removed out, okay, micro level. So, that micro level particle 1, 2, 3, 4, 5, then after a certain time you see lots of erosion happened in the pipe. So, erosion happened means leakage and bursting possible. Okay, again noise will be possible, very high velocity fluid passing through the through your system, your pipeline, then a flow noise will be coming up. Water hammering also will be possible. Suddenly any flow blockage is there, water will be hammered. You see you have one vertical pipe, okay, very high pressure fluid is moving. Now suddenly you close the valve, what will happen? All the momentum will be acting on the pipe, so pipe can burst actually. Okay, fluid is moving at rushing at very high velocity, suddenly close the flow path, or because of certain reason flow path got obstructed. So because of that, water hammering will happen. Water hammering means the whole fluid column will be acting as hammer, and it will be breaking the fluid pipeline. Surge, sand, other solid transport limits minimum. Okay, so surging will be happening if you have very low fluid velocity, sand and other solid particle if there in the pipeline, so that will be getting deposited in the pipeline. So that will be one big problem. When fluid is flowing through a pipe, there will be erosion. Okay, erosion formula is like this: VE equals C by rho m power half. Okay, so what is C, what is rho? V is the erosion velocity, feet per second. C is a constant, empirical constant. Rho m is your density of fluid, Normally it will be used for two phase flow, that is why rho m is given. So average density of fluid will be used. So LB per cubic feet. Okay. If velocity exceeds VE, erosion of the product of will be happening, and if corrosive fluid is there, then it will be much more disastrous. In 1990s, API gave some value of C. So they said C value should be 150. Okay, for continuous service, okay, and for 200 for non-continuous service, non-continuous service. Okay. So erosive service of solid present, erosive service. Okay, so this formula is given by SWRI. So SWRI said like upper formula may not be applicable everywhere, so they have derived another formula called erosive service for solid, if solid present in the flow without corrosion, Okay, so formula is that VE KS D root over QS. Okay, for erosion, the erosional velocity can be determined by the above equation. Okay, this is called erosional velocity VE. So KS is a fitting factor. So it will be obtained from certain table. Okay, D is pipe inside diameter in inch. QS is solid or sand flow rate. sorry, it may be sand, okay, and unit is FTQ per second, per day, not second, per day, okay. And this formula is given to Southwest Research Institute, US, West Research liquid line. Say you are designing a pipeline, it's carrying liquid. So, in that case, maximum velocity will be about 15 feet per second for a line sizing to minimize noise, water hammer and erosion. Sand grain deposit on the bottom until equilibrium velocity is reached. What happens? You have one pipe, okay. So, if you have very low velocity, so sand will be deposited, okay. Now, you increase velocity, what will happen? This high fluid velocity, it will be trying to eroding this sand, whatever deposited there, it will be trying to eroding, okay. And again after certain time, it again one equilibrium condition will be coming. So, X amount sand will be getting deposited, same amount will be moving out, okay. So, in that case, there will be no extra deposition, rather certain amount deposited, certain amount is getting removed. But again, you reduce fluid velocity, again certain sand will be deposited and again equilibrium will be maintained. So, that equilibrium maintenance will be working if you are changing fluid velocity, but at very high velocity erosion rate will be higher. So, there will be no deposition, almost no deposition. So, if V is increased, bed eroded to reach new equilibrium velocity, V means velocity, again it will be stabilizing, okay. If V decreased, again some more accumulation will be there, again establish equilibrium will be coming up, okay. Minimum V velocity, velocity of fluid can be 3 feet per second, they are normally recommending, okay. Okay. So, fluid velocity V equals 0.012 QL divided by D square. So, pipe ID and QL is the liquid flow rate. This is barrel per day, or BPD I can write, BPD, okay. And this is in field unit. Okay. Now, erosion of metal, formula is the volume equals K W V square beta G by P. So, K erosion wear coefficient, okay. W is equal total weight of impinging sand particle, and V is the particle velocity, I am putting equal sign, okay, particle velocity, P penetration hardness of the material. This is P is not pressure, penetration hardness. So, here hardness is how much hard the metal, because how the test. So, they will be taking one specimen, like say one metal is taken and one small like diamond shape or triangular shape, some other solid strong metal, they will try to push it down. So, how much indentation happening here, so they will try to measure. So, that way it will be showing how much hardness is there, okay. Sometimes this will be like diamond shape, sometime it will be like circular shaped, okay. Circular shaped on one tip you take and you try to push it down. So, how much penetration happening because of certain pressure, so that will be the measurement of hardness. So, that is called penetration hardness, okay. So, there will be different method, Charpy method is there, Brinell hardness testing method is there. So, different methods are there, using the material scientists, they will be measuring the penetration hardness or hardness values. beta, a value between 0.5 to 1.0 depending upon the impingement angle, depending upon the impingement angle of the particle. Okay. So, pressure drop, there is one figure, operating pressure, and this is pressure drop. Pressure drop per 100 feet psi. Okay. So, the curve will be like looking like this. So, if you are changing operating pressure, then how the pressure is getting changed, you can get from this curve. So, this is called figure acceptable pressure drop, or I can write del P or del P. Okay, acceptable pressure drop for short lines. For long lines, the curve will be different. Okay, for gas line, the formula will be a little bit changed. So, if V is a V or velocity is the major criteria. Velocity is the major criteria, del P is not a much problem. Okay, del P due to friction recovered by recompressing. So, if there is any loss in del P, so again compression should be done. Minimum velocity 10 to 15 feet per second to minimize liquid settling out from the low spots, or through pipe fluid is going, and if there is any liquid particle, it should not get settled out and should not get blocked. If there is lots of liquid settling out from the gas, so that will be blocking the flow path. So, maximum velocity can be 60 to 80 feet per second to minimize the effect of noise and corrosion. Okay. So, VE erosion velocity 0.6, C is a constant, erosional flow constant, and S is specific gravity of gas at standard condition. Air equals 1, air specific gravity is 1, P is the pressure, psi, T is Rankine temperature. Okay. So, VE equals 0.6 C T by SP. Okay. So, here we assume Z equals 1, compressibility is 1. Okay. Erosion velocity to a small amount of liquid in the gas can be calculated here. Okay. So, erosion velocity for small amount of liquid can be calculated using this formula. And another formula is there, d power 5 1260 STF QG P by del P. So, what is D? D is pipe ID, S is your specific gravity of gas, T Rankine temperature degree R, QG your gas flow rate, P is your pressure, PSIA, del P again pressure drop PSIA, and FTF Moody's friction factor. F is Moody's friction factor. Moody's friction factor. So, from there we can calculate a diameter. and detail of the formula we will be using later. Two-phase flow. Most two-phase lines operate at high pressure, and pressure drop is usually not used to calculate a diameter. Recommendation: minimum velocity will be 10 to 15 meter per second to keep liquid moving in the line to minimize slugging. If liquid is getting deposited, then there will be a problem. Okay. Slugging of separator, other process equipment. Maximum velocity should be 60 feet per second for reduction of low noise, 50 feet per second for inhibiting COT corrosion and or other erosional velocities. So, 50 to 60 maximum velocity can be kept. Okay, erosion velocity expressed as for two-phase flow, erosional velocity. C by Pm. C is constant. Okay, rho m is your density, and then okay. Okay, the density of the mixture, the density of the can be expressed as rho m 12409 specific gravity into P 2.7 SRP 198.7 P ZRT. So, the terms are SG specific gravity, P is your pressure, and S specific gravity, this is specific gravity of liquid relative to water, use the average gravity for hydrocarbon and water for mixture. Okay. So, SG use average gravity for hydrocarbon and water mixture. Okay. R is gas liquid ratio, R gas liquid ratio, and what term is there? Z is compressibility factor. S is specific gravity of air 1, a specific gravity of gas air equals 1. Okay. Okay, thank you very much for today's lecture. Next day we will try to solve some problem. Thank you very much.